Testing. Okay. Hello. Assalamualaikum. Boleh dengar saya tak? Zami, Denny. Okay, siapa yang mic dia off boleh on kan kot. Okay. Arif, Ain, Kuget, Okay, so berapa orang? 6. 6 orang. 5 orang
5
orang. Ada lagi tak?
Ada 2.
Any foreign student here?
One student.
Should be one above.
Hiba foreign student? Okay. So Zanzame, Denny, Arif, Ain, Kugeran, and Hiba. Alright. So before while we wait for your friends, okay, to enter, okay, just let me introduce myself. I'm Dr. Mariam from Mechatronics Department. So I'm going to teach you system dynamic, okay, which is part 1, 2, and 3 for modeling, mathematical modeling for dynamic system. Okay, so if I'm not sure why I'm doing the explanation today for class, because this is the first time e-learning. I'm not sure if you have taken any e-learning class, but if you do not interrupt me, I'm going to like very fast explain everything. So if you do not understand me, please just ask question lah. Okay? Right? So I prefer student to ask question. Right, let me just adjust the whiteboard. You see the whiteboard, right? Because today we are going to do some mathematical modeling, and most of the exercises will be on derivation. Okay, so can I get some of you guys to introduce yourselves? Where are you from? Graduated from which university? And is it that before this you have experience working and so on? Right. So can we start with Zamzame?
Okay. Can you hear me?
Yeah, I can.
Okay. My name is Zamzame Besain. I'm from Kajang, Selangor. Previously, I graduated from University Malaysia Police.
Okay.
And have no working experience.
So means that you graduate directly from UNIMAP, is it?
Yeah.
2019.
No, 2010.
2010. So before this, were you working somewhere?
Working not related to the mechatronic engineering.
Oh, okay. All right. All right. Thank you. Okay, next, Denny.
Yeah, is my voice clear, Doctor?
Yeah, I can hear you.
Yeah. Okay. My name is Denny Ding, anak Jimmy.
Okay.
From Sarawak. Previously graduated from UTM, Mechatronics Engineering, last year.
Okay. Okay. I think I never seen you before.
Yeah, but I see doctor a lot.
Oh, you saw me a lot.
In
Okay.
FKE, yeah.
FKE, but I think I never teach you. Okay.
Yeah. Doctor never teach us.
All right. So next, Hanif Rahman.
Assalamualaikum, madam. My name is Muhammad Hanif.
Okay.
Previously graduated from degree Mechatronic Engineering. Same with Denny also. Live in Melaka, that's all.
Okay, Melaka. All right. Arif, your mic is mute. You don't have any mic.
I do have. Can you hear me?
Okay, you have mic. Okay. Just introduction bit.
Okay. My name is Ahmad Arif, and I'm also graduated from UTM, Mechatronics. I'm from Michigan. You know a lot about me, right? So because you're my team.
Okay, yeah, I know. Okay, right. Next, Ain.
Hi, my name is Ain. Previously degree in civil engineering and from KL.
From KL. Okay. Next, who's Kugan already?
Not yet, madam.
Not yet. Okay, Kugan.
Okay. My name is Kugan from Kulim Kedah. So previously I did my degree in mechatronic engineering at UTM also. I don't have any working experience.
Okay.
Yeah, except for the LI training.
LI training. Were you? Yeah. I think I went for your LI training last time was in Penang.
Yes. Yeah.
Penang.
Yeah, Penang.
Okay. Alright. Sounds familiar, your name. Alright, and Shadik?
Assalamualaikum, my name is Muhammad Shadik. Previously taking degree in Mechatronics Engineering in UTM, and I'm from Sabah.
From Sabah, okay. Alright, next, Hanif already, Heba, last but not least.
Can you hear me?
Yeah, I can hear you.
Okay, I'm Hiba from Palestine. I graduated from Palestine Technical University Khadouri. And now I'm studying here master.
Okay, all right. So nice.
Yeah, but I have one question. I have meeting today at 5 p.m. Can I know when will we finish that class?
We finish roughly about 4:30.
4:30.
4:30. Since actually, as you know, the class should be 2 days per week, right? And 2 days full. But because I'm going to cover 3 chapters, so which is system dynamic, modeling for dynamic system for spring and damper, first part, which is I'm going to teach you today, and second one is electromechanical system, and third one is fluid and thermal. So there are 3 main chapters. So for today is that I'm going to try to finish the first part, which is spring and damper in mechanical system. So hopefully by 4:30 lah. If we do not finish by 4:30, then maybe we need to find another slot for this. Okay, since it's a E class, so I think there's no problem to actually find another slot. Okay. Kugan belakang tu siapa? Oh, you housemate.
Arif. Ya, Arif.
Okay, belakang dia ada seorang lagi you punya. Okay, housemate. Alright. So let's just start this class. So everybody download the notes.
Yes.
Already, okay. So I'm going to what you are going to learn today is that basically an expansion of what you have learned in control system engineering. Okay, so control system engineering, control 1 and control 2 is that you learn about how to do the mathematical modeling for the system, and you only learn about mass spring damper and also electromechanical system. For the master course for today is that you're going to learn those 2 parts, and also another one is on fluid and thermal. Okay, so I'm going to be quite fast because you have the background of dynamic modeling. So, but if you find it too fast, please just inform me. Okay, just interrupt me, right? So let's go to the first part, which is first one is that if you see the first page here, the notes that I have here is adapted from these. Okay, wait a minute. Okay. Okay, the notes that I'm updating is from 4 main textbook. The main one is this one, Dynamic System, William Palm. So if you have the time, please go and borrow it from library. If not, you can find it online. There's an e-book link to download the notes online. So I'm going to refer maybe about 80% from this book. Okay. Second book is from Control System Engineering, Normal Nice. So Normal Nice book is the normal, is the common book that you referred during undergraduates. So Normal Nice. Third one is Dynamic System, which is OLATA, which is related to the first reference book here. And the fourth one is actually, I'm referring to some of notes from Dr. Norafiza Abbas on undergraduate notes, but just a little bit, like 4 to 5 slides only. Right? So let's just go to see what are the learning outcome that you are going to achieve by the end of this topic. For part 1, part 2, and part 3 is to derive the mathematical modeling of dynamic system in frequency and time domain. Okay, so means that what you're going to learn today is that to introduce the method for predicting dynamic behavior of mechanical system. Example, you have a spring. So how do you actually model that that system? Okay, so you can have either mechanical, electrical, fluid, and thermal elements. So this is what you're going to learn for this week class with me. Okay. And if you see here, after the course, you'll be able to build mathematical model of physical system for the first principle. It's mostly our second order. Second one is analyze behavior of system using built model, mathematical model. So this is where after you model everything, you come up with a transfer function, and then you're going to convert it to a Simulink or MATLAB, Simulink block using MATLAB. And lastly is that you're going to use the software tool, MATLAB or Simulink for modeling, simulation, analysis. So I think most of you are doing project 1 for master, correct?
Yeah.
Yes, right? So if you're doing some sort of research on controller, okay, you're going to have a system. So the system might be a mechanical system, a combination of mechanical and electrical. So it's an electromechanical system. So you have mass, you have a damper, and so on. So how do you actually represent that system into a simple system? So this is what you're going to do to model it into a transfer function. Okay. So below here is that you can refer to the link that I gave you down here. Okay. So if you see here, there are lots of parts under the part 1, spring and damper. We have 8 main topics. So overview, just to be overview, what are spring element, modeling mass spring system, what is damping element. Okay, you have learned about mass system in the previous last week with Dr. Norafiza, right? So now for today is that you're going to continue to do modeling for mass, spring, and damper system. And then energy method is that I'm going to actually explain briefly about what are the equation used for energy method when you have all this spring, mass, and damper. And lastly is on MATLAB application. So after you have learned from the first part here until the part 7 here, you learn that you can actually come up with a transfer function. And from that transfer function, you're going to convert it into MATLAB application. So you're going to do the modeling. A system, you have input, you have an output. So how you do model it? If the input is a step input, so what are the response of the system? Right? Okay, next is just an overview. So a system is a collection of components which are coordinated together to perform a function. Right? So a system is defined part of the real world. So you have a system, so we are going to simplify it. Okay, simplify into what are the input to a system, what are the input, and what are the disturbances. Okay, example, we take a very example dynamic system, aircraft, car, a robot, and antenna position. Okay, so For example, we take a car, example of a car. The car, what is the aim of the car? To actually control the speed of the car. So what are the input? Any idea? You guys can respond, eh? What are the input to a car if the output is the speed? Pardon?
A fuel.
The fuel.
Fuel.
Fuel, yeah? Okay, the fuel means that the acceleration, right? The fuel means that the pedal. Okay, input is the fuel, which is the input, a signal or something, a pedal. Okay, so that one, a car is normally an open loop system because you do not have any feedback. You have a feedback. The feedback is actually the human, doing all the feedback. You control it. If you're near to the front car, then you press the brake pedal. Okay, if you have a distance, then you will actually speed up. So the human is the one who are in control. But if you talk about a system that is actually a closed loop, okay, closed loop. Example, right now we have a car that have a closed loop dynamic system. So example is Tesla. Tesla is autonomous system. It means that drivers just sit inside the car, don't need to do any acceleration on the pedal. Okay, so this is example of a dynamic system. But if you're talking about a car, that will be much more complicated system, right? So dynamic system is a system with memory. You have the input value at time t with inflow for output future instant. So you have a output with that is changed over time. Okay, so let's just look at what are the modeling steps. Okay, there are a few steps to do this modeling. So if you see here, the first one is, step one is to determine what are the physical system, what are the requirement. Okay, requirement means that what are the input to the system, what is the output. Example, we take a simple example of a motor, DC motor. The DC motor, the output is a rotation. So but when you want to rotate the motor, what happens is that you need to have the input, which is a voltage input. Okay, so you determine what is the input and what is the output. And from there, you need to determine what are the dynamic of the motor itself. So what's inside? You have mass inside. The rotor is the mass. Okay, what else? Do you have a damper inside? And so on. Okay, so that one is the first step. Second step is to draw the functional block diagram. So after that, draw the block transfer function. Okay, and then third one is transform the physical system into schematic. And fourth one is that obtain the signal flow graph and so on. Okay, and lastly is that if you want to make it convert it into a closed loop, then you need to actually convert output will have actually the output compare with the input, then you will get an error, right? So, and then you see what are the output response. Example, you want to see the response of the motor based on what reference that you set. Okay, reference 10 degree and 10 degree, 40 degree, and so on. Okay. So this one is example. You have antenna. So the antenna here is connected to a motor. Okay, this motor. And you have learned in the previous chapter with the Torsional is that when you have a DC motor or output or torque, we call it as the inertia, you connect it to a gear ring system. And the reason that you add it to a gearing system is that to increase or reduce a torque value. Okay, so you have the motor connected to a gearing system and it will actually rotate the antenna. And then you have the input azimuth here as the input reference. Okay, so if you look at this schematic here, okay, schematic, you will see that this system, this schematic represents this system. You have the input azimuth here, you have the dynamic models inside here, you have the motor, you have the amplifier, you have the pre-amplifier, the armature here, which is, this one is the motor transmission of the system, and then you have the gearing. After motor, you have the gearing here. So you see that there's a gear N1, N2, N3. Then N2 gear is connected to the load which is the inertia JL. So we have JL here, and then it will actually give the output to the azimuth antenna. Okay, so this from here is that you convert it into a block diagram. So when you convert it to a block diagram, you can draw this out again as the plant of process itself, motor, load, and gear as one block. And then you have the controller, signal, and power amplifier, which is this part is the controller part. Then, in order for you to read what is the output angle here, you need to have a sensor, which is the potentiometer. So it will read what are the angular output. Okay, so this output will be compared with the reference that you set. So this reference that you set is actually the reference of the azimuth angle that you want. For example, you want to rotate it 30 degrees. So you set the degree at this end part, front part. Okay, so the idea here is we're not talking about everything right now. Okay, later on you are going to learn about everything from the input until the output with a closed loop with Dr. Chong next week. But my part is to explain only on the mathematical modeling of the dynamic system here for this part, plant or process. Okay, everybody okay? Am I too fast?
Okay.
Okay, all right. While I'm talking, I think it's better to jot down something, or well, in the end, after I have explained everything, I will also upload this video to Yulen. Do you have Yulen for master? Do you have Yulen? Ada. Okay, so I will upload this video to Yulen or to my YouTube lah. Okay, to my YouTube, so you can actually view it many times if you want. Okay, it's just for class purpose and not for everyone else. Okay, so let's continue. Okay, so we go to the first part, which is the translational mechanical system. So translational mechanical system is about a mass that is moving in the horizontal position, horizontal or vertical position. So example, you have this mass value, mass. So translation means that it's going to move in linear position. It's either in this axis, x-axis, or in y-axis. So this is what we call as translational mechanical system. Okay, and from here you can see that we have the we can actually represent it as in terms of mass, damper, and spring. So you have learned about mass in last week. So you have mass, damper, and spring, and this one is represented as the component spring, xt, F as a force. Okay, so imagine that if you have a spring, okay, you pull the spring, then when you pull this direction, you have the spring, this is fixed area, you pull it to the right, then this is the force direction, and the direction of the spring xt is also the same as the force. Okay, so you can actually write that equation as this force displacement ft equal to kxt. Okay, k is the coefficient for spring. Okay, and for viscous damper is same thing. You have a damper force, you pull it in one direction, xt will be the same direction as a force, so it can be written as the differentiation of xt. So you get ft equal to fv dx dt. And for mass is you have ft equal to m dx squared equal to dt. Okay, and by comparison, okay, you also have the rotational mechanical system. There's a function. So imagine that this one, instead of a mass, is actually a rotational system, or motor just now. It's going to rotate. Instead of moving translational or linear motion, okay, so it's going to rotate at this axis. Okay, so you can represent this as a spring, viscous, and inertia. So let's take it as, instead, let me draw that first. Here you have mass, you have C, and then you have K. this one is for linear motion. Can you see the whiteboard? Is it clear?
Yes.
Yes.
Okay, this is linear motion and this is rotary motion. Okay, rotary motion we have J, which is inertia. C, we have the they are using D, and then for K, they are using spring. K juga, okay. Alright. So for linear motion is that the representative of the rotary is that J, inertia, and this is mass, and C is represented by D, and spring is using K value. So if you see here, okay, you can write out the equation as this equation here. So T, K, theta, which is the output. So this one, the output is XT. We write out in this space there, so we can write it in X double dot, X dot, and X, and we have J theta double dot, D dot, and K theta. Right, so that is how you write out the representation of the rotary transfer function. Okay, now we go to the spring element. Yeah? So spring element is that, just a recap, so mass is assumed to be rigid where object motion is relatively uncomplicated, simple translation or simple rotation. So I just explained just now that mass and J, okay, can be represented as a simple translation, linear motion, or rotation. But however, many applications mass deforms under action of force or connected to another object by element of deformation. So because of that, you need to have the spring element. Okay. So example of a spring element is the helical coil spring. So this is example of helical coil spring. So we have the K value. So F is equal to FKX. So purpose here is that provide a restoration force. So example of a helical spring, coil spring is that you can see a very simple example is in your pen. Okay, pen. So in your pen, you have spring. You have a spring inside here. That's why when you actually click it back, it will actually restore to the normal position. Okay, so that one is a very simple example of a helical spring. Okay, but in reality is that you have a lot of spring constant. So these are the spring constant of common element. So you have first one is the helical spring, second one is the solid rod, and next is a supported beam, fourth one is a cantilever beam, and fixed beam, and last one is the leaf spring. So if you see on the right hand side of each of the component is that you have the spring coefficient K, and it's given by different value. So but initially for the normal helical spring is that F is equal to Kx. So this K value can actually be changed to this pointer pen. Can actually change to this one K value here. Okay, so this K value depending on what spring type that you're using in that system. Okay, so let's go to the first one. So you have a deflection, force deflection. So for linear force deflection model here is that you are using the Hooke's law. So the force is given by Kx. Okay, X is the extension distance, compression or extension distance. K is the spring constant. Okay, and the force is the unit Newton over meter. Okay, so L, if you see based on this figure is that the L is the free length of the spring when there is no compression. Okay, so where there is no compression, L is this value. Okay, when there is a deflection, then you have a restoring force. Okay? So if you derive this equation is that you will actually find out that you have G equal to GD to the power of 4 over 64 and R3. So D is the widest diameter, R radius of the coil, so radius of this coil, and number of coil, G shear modulus of elasticity of the material. So this one is going to be more detailed compared to the previous equation that you have known before, which is F equal to Kx. So K is actually for K element spring is given by this K value. And for the solid rod is that, okay, example here is derive the spring constant K, okay, for a solid rod, expression for a cylindrical steel rod subjected to tensile or compression. So meaning that if you have a rod here, okay, so you actually compress it, okay, compress it or you pull it, so it actually represents a spring element. Okay, how to actually get the value of K is that, okay, we start first with this F equal to Kx, and then we find out that K value is EA over L. So how do you find this? So E is actually the modulus of elasticity of the material itself. So what type of material you are using? A is the cross-sectional area, so this area, and L is given by the length, okay, of the rod. So you get K equal to EE over L. So from here is that you can actually substitute it, then you will get X equal to L over EAF, and then you get this. Then in the end, you can derive F equal to EA over LX. Then you get this one as the spring coefficient. Okay, so that's why for the solid rod here, if you see here, you can directly get K equal to EA over L. Okay. Yes, anyone is want to ask question? No? Okay, so not yet, okay. That's good. Nobody is sleeping, Nobody sleeping?
No.
Nobody go out, Not yet, Okay. So we try to do this e-learning class lah. I'm actually talking without looking at you, So I'm just like talking to myself. Right? So let's go to one example shown here. What is the tensile test of a rod? So you have a rod here, okay? Given you have already derived just now, K equal to EA over L, okay? And A is given by the cross-sectional area here. Okay, let's see that you have the plot area here. Okay, plot of a tension test data. Okay, you plot the data. Okay, linear means that, what does it mean by linear? Linear means that when you pull it, okay, it will actually, when you actually pull the rod, it will actually go back to the original position. Okay, means that if you were to pull it, it will actually go up to this point and then it go back to the same point again. But if you see here, okay, there are two lines, increasing and decreasing. Okay, what does it mean? Okay, what it means that, example, imagine that you have a spring just now. You pull the spring until it's actually deformed. Okay, when you release it, does the spring go back to the original position? No, because it's already deformed. You already pull it more than the K value. Okay, the modulus means that the K value you already calculate just now. But if you pull it more than the K value, then if you release the spring won't go back to the original position. So this is what it means. If you pull the rod here until it is hit this point, okay, elastic limit here. Okay, what happens that you will pull it and then it will go to this saturation point. After you release it, it will go back to the initial point. It should go back to the initial point, but because of you already pull it, exceed the K limit, then it will actually it will actually go back not to initial point at 0, but it will have an elongation at 1 cm. Okay, not 1 cm, 1000 of cm. So this one what we call as permanent elongation. So means that you already break the material. So you have a solid rod or a spring, you already break that rod or spring. Okay, so means that if I were pushing this spring more than what K value, then after I release it, it won't go back to the original position. Okay. So we skip this. Moment of inertia is what you have learned before. Okay, moment of inertia is that when you have a mass, so mass moment of inertia is angular mass or rotation of the inertia. So you have the inertia, it either rotate in this point, or it rotate this point, or rotate this point. Okay, so based on this, that you will get the I value. Okay, next we go to the spring element of fixed N versus cantilever beam. So this is still under spring element. So you see on the left side is a fixed N beam. So means that you have two sides is fixed here. Okay, you have a beam. Beam should be actually straight lah. Right now you are giving a force downwards, so that's why it's actually have a X value, deflection value here. Okay, and another one is that on comparison is that you have a cantilever beam. Cantilever beam is that you have only one side is fixed, another side is not fixed. Okay, so these are the parameter of the fixed N and then cantilever beam. So from here is that you can actually calculate what is the K value, okay, and what is K value for cantilever. So if you see here, actually the fixed beam N is 64 more times, much more stiffer than the cantilever beam. If you see here, if you actually divide it, you can actually see that fixed beam is actually 64 times stiffer than the cantilever, which is true lah. If you see the system itself, which one is much more stronger? Of course, the fixed M beam. Okay. So example, if you see this one, this photo, what type of beam? Is it fixed beam or cantilever beam?
Fixed
beam, right? Also have two sides. Here fixed and you have the beam here. So this one is actually example of a spring system. But have you imagined that when you are driving on the road? Maybe no, okay. And then this one is a other different type of cantilever beam. So you see that this one is a structure that have a beam on top and two fixed beam below, and then you have a house at the end of the cliff, and then you have here is airplane, okay, the wing part. Then you have this one, the parking lot, okay, and this one may be something like a view, top. Not sure what it is, but anyway, you go on there and then you can see from far. Okay, so this one is example of cantilever beam. Okay, so the wing part, airplane, and also this parking space is example of cantilever beam. Single overhanging means that you have two fixed part and you have another one part overhanging at this end part. Okay, and for double overhanging is that two parts is actually overhanging at two fixed part in the center, right? Yeah, I'm just want to show to you, to share to you something. Have you heard about have you heard about the iron ring? Have you heard about this iron ring?
No. No.
Iron ring? No. Actually, iron ring is something that engineer in Canada, they wear it. They actually receive an iron ring, like iron ring after they graduated from university. So it represents the ethics as an engineer. Okay, it's actually there's a history behind it. Okay, what happens is that this iron ring is given to those graduated in Canada University. So what happened is that the ring is made from iron. Okay, but lately they are made it from stainless steel because of the corrosion of the iron. So when people wear it, your hand become black. Okay, so the history behind it is that the cubic bridge. So maybe you can Google this. Okay, cubic bridge. What happens that this cubic bridge was built, okay, 2 times. It's actually crashed, okay, due to the engineer that actually designed this bridge because of the miscalculation of the beam here. Okay, the beam, if you see here, the cubic grid design. So you see that this is the design of cubic grids, which is actually a fixed beam or cantilever beam type. So you have 2 fixed beam here at this side. So what happens is that halfway through building this, this part actually deformed and the beam crashed into the ocean. So this bridge took 30 years to actually build it. And during that part, that design, the building part, 88 engineer died or workers died because of the miscalculation of the engineer. So that is what happened. They actually gave the ring. The ring was made from a part of the bridge itself. So from iron material. Okay, so means that if you become an engineer later on, are you going to become engineer later on? You guys? No? Hopefully. Okay, so if you become an engineer, make sure that you calculate it correctly. Okay, if not, you're going to actually make people lost families and so on. Okay, you can try to Google that. Okay, so let's continue. Okay, so next is the leaf spring. Okay, leaf spring is, anyone heard about what is leaf spring?
No.
Anyone know what is leaf spring? No.
Car suspension?
Yes, correct. Car suspension. Who answered that?
Danny.
Danny, okay, correct. That's correct. Okay, you see here, this was an example of a car suspension. Okay, so this is under a lorry. Okay, so you have the leaf spring here. You have the axle here of the tire, and then it's connected to the body or frame of the lorry. So the spring, the K spring is expression of L thickness of H. So you have L length, thickness of H here, and width, assuming that force and deflection are at the center of the beam. But if you see here, the spring for vehicle suspension are constructed by strapping together several layers of springs. So means that if you see here, example, I have the first layer of spring, second and third. So this one is being strapped together, so you get a leaf spring there. So how to calculate that is that there is a calculation how to do that, because each spring it might not be having the same width and height. So, but anyway, for the calculation of K for the spring is that is given by this value. Okay, this value K equal to E 2E WH to the power of 3 over L to the power of 3. So E is the modulus of elasticity of the material itself. Okay, what time is it? 2:35. Can we take a 5-minute break?
Yes.
5-minute break. I'm going to stop it for a while because I can only do this online for 40 minutes now. Okay, and then because I don't have I didn't actually buy the Zoom.me, so it's free version. So free version is only 40 minutes. So I'm going to stop and then we come back at 2:45. Is it okay?
Okay.
Okay. All right. Thank you.
Yeah.